Hi class, welcome to lecture 5 for statistics. We're going to start talking about hypothesis testing, right? This big idea that we kind of have been working towards so far this whole semester because we're taking data and numbers and we're using that to answer questions that we are hypothesizing as psychological researchers. So that's pretty exciting. We finally made it to the part that maybe you thought we would be doing in statistics. So I'm going to share my screen and share lecture 5 with you from the beginning. All right. It's like 2317, unit 5. So we're going to answer research questions by translating them to statistical questions. We're going to learn how to construct a confidence interval, and then we'll talk about the basics of hypothesis testing, the null and the alternative hypotheses. So we'll stay with our example, our theme for this semester. Suppose we are testing a treatment that's been proposed to increase IQ scores. So our sample has an N of 25. They're given the treatment, and the average IQ score for our sample is X bar 107. So I'm a researcher. I have this hypothesis that if I do this thing with, say, sophomore college students or college students in general, I could increase their IQ score. Some intelligence um, tutoring or um, treatment that might help increase their IQ. And I think that if I can, prove that this works, then I can help students everywhere have higher IQ scores. So I do my intelligence experiment and treatment on this one group, and I had 25 people, and I get their scores at the end of my 6-week IQ treatment, and their scores mean is 107. So did my treatment work? Well, that's a great question. How do I know? We have to answer this hypothesis, this theoretical question in by answering a statistical question. So we know that the average IQ for the general population is 100 with a standard deviation of 15. That's just a well-known fact, and we need to know the population mean and standard deviation. So mu will be the mean of the population who receives the treatment. So now we are asking, is mu bigger than 100? If the general population has a score of 100, is my mu, is it bigger than 100? The people who received my treatment, did they get a higher score? I could answer it one of two ways. I could estimate mu from X bar, or I could compete two hypotheses against each other about mu. So I'm going to show you how to do both of them, and then we'll talk about which one we'll probably use going forward. So method number 1 is estimation. We'll estimate something called a confidence interval. So remember from all of our previous lectures, right? We know that 95% of the sample means are within almost 2 standard deviations of the population mean. Well, almost, right? Let me get a highlighter here. So if we have mu here in the center, right? We have the center line here, and we have the standard deviation. We know that where 2 standard deviations are, the center here, right? This is 96% of my bar here, and then another 3 point something percent, right? So if we added up from this line to this line, and we added up everything that fell between these two bars, it would be 95%. So there's a 95% probability that any given sample means is within mu minus 1.96 and mu plus 1.96 because the 3 things that we know about our distribution, right? We're assuming that it's normal. We know that the standard error is this formula right here, standard deviation divided by square root of n, and that's what's controlling the width. And then we know that it peaks at mu. Those are the things that we know to be true. So because we know that this is 95% exactly, we know that if we wrote that out as a statistic, it would look like this. Mu less than 1.96 on this side and mu plus 1.96 on this side. So there's a 95% probability that any given sample mean lives within this section. So what does that look like in numbers, right? I just said a lot of words, but this is what it looks like in numbers. Mu minus 1.96 times standard deviation above square divided by square root of n. So here's our mu right here in the middle, is less than this side and is more than this side. Sorry, not less than, more than, that it's between, right? That it's, this is the lower limit and this is the upper limit. So if we use a little bit of algebra to move things around, right, to move this over to the center and to move x bar over here, then we have x bar minus 1.96 times standard deviation divided by square root of n is less than mu, which is more than, it's more than mu and less than x bar plus 1.96 times standard deviation square root of n. That's a whole lot of words. What am I? Whole lot of words in a really big equation. So what am I saying? Interpreting this, there is a 95%, not a 95% chance, right? We're not talking about probability. We're saying that we're 95% confident that mu is between these two scores for my given interval, for my given example. So for this example that we started with, our n of 25 had a mean of x bar 107. So if we computed a 95% confidence interval for this mu, it would look like this. 95% confidence interval equals, here's our really long big equation. So if we put in all the numbers, which we have, we get 107 minus 5.88 on this side and 107 plus 5.88 on this side, right? It's really two separate equations. And so when we get the answers for each one of those, we get minus and we get plus, which gives us these two numbers right here, 101.12 and 112.88. So what does that mean? Well, these are our upper and lower limits. So we're saying we know that the standard deviation for IQ scores in general is 15. There's a 95%, I'm 95% confident that my score is between 101.12 and 112.88. So this, for this particular example, this 5.88, we're going to call this the margin of error. It has a term, right? The margin of error. We're 95% confident that the mean IQ of the population of individuals who received my treatment is between 101.12 and 112.88. So how does that answer our question? Well, since mu is greater than 100, I could conclude that the treatment worked. Awesome. They got a higher IQ score after my intelligence training than the IQ score of the general population. So that's super exciting. We concluded something that we now know from something that we didn't know. Awesome. What about the other way? What about hypothesis testing? So hypothesis testing is giving us a similar answer, right? It's turning our general question that we're trying to assess into an equation, into a statistical question, but we compete two hypotheses against each other regarding mu. So we have a null hypothesis and an alternative hypothesis. The null will be notated like this moving forward, right? It'll be H0. So that says that mu equals 100. It's called the null hypothesis, meaning null, it didn't work, right? The treatment had no effect because we know that the population has a mean of 100. So I'm assuming under this null hypothesis that mine also has a mu of 100. And if mine is the same as the general population that didn't get the intelligence training, then it didn't work. There was no success in my treatment, no effect. But alternatively, this alternative hypothesis can be notated with H1. It says that mu is greater than 100, that there was a positive effect because my treatment did work. It increased their scores. It doesn't always have to be greater than. It could be less than. It could be is not equal to. It just depends on the question that you're asking. But for this specific question, we're seeing if scores were increased, right? If people were more intelligent, if their scores were higher. So that means if I want scores to be higher, mu is greater than 100. That could be the alternative hypothesis. So it's kind of backwards land to figure that out, right? To move forward, we're going to assume that the null is true. We're going to assume that our treatment had no effect. And that seems backwards, right? Because we as researchers really did hope that our treatment did have an effect, and we assumed there would be an effect, or we wouldn't spend all of this time and money researching this thing. But for statistical purposes and ethical reasons, we're assuming that there is no effect. So moving forward, we're believing that the null hypothesis is true. Mu is equal to 100. Well, this is important because now it gives us a number to work with. What's the probability of observing our sample mean of 107 or higher if the null is true? So if mu really is 100, what's the probability that we would get 107? Let's find out. So statistically, that looks like probability that X bar is greater than 107. Well, hopefully that looks familiar. Hopefully that looks like the questions that we are answering in Unit 4. So you should know how to do this. You should know how to answer this question, right? We have to compute a z-score. So we can compute a z-score because we have a distribution of sample means. So that formula was here, right? Z is equal to X bar minus mu over standard deviation divided by square root of n, right? This was the standard error. So when you compute those numbers out, you get 2.33. So P, Z is greater than 2.33 equals 0.009. That seems like a really, really small number. What does that mean? So we could interpret that by saying the probability of obtaining our sample mean if mu equals 100 is 0.0099. Well, that seems really rare, right? That's less than 1%. So that, since our data would be really rare, assuming the null hypothesis is true, we can now reject the null hypothesis, and we can conclude that we have support for the alternative hypothesis. We reject the null as plausible and in turn choose the alternative, right? Because when if there's only a point less than 0.1% chance, that seems really rare. So there's no way that's true. We're gonna say there's no way that's true, and we're gonna say our treatment worked. How exciting is that? So when P is less than 0.05, we reject the null hypothesis and conclude there was a significant effect. But if P is greater than 0.05, we fail to reject the null hypothesis and conclude that the effect was not significant. So because what we got here is less than 0.05, we reject the null hypothesis. If we would have got a number here that was more than 0.05, we would have failed to reject the null hypothesis, which is the same as saying we're accepting the null hypothesis, but that's not how we say it in statistics or in psychology. And read any scientific journal article in psychological sciences, and they'll say that we fail to reject the null or we reject the null. But you won't ever say like we found support for the alternative. We don't say it that way. We say we fail to reject the null or we reject the null. It seems like a backwards way of thinking about it, but that's just how we do it here in psychological sciences. So what's my take home? To answer research questions, we have to turn them into statistical questions about some population with a parameter like mu, like a mean. So we could do it the two ways, right? The first way was estimation and the second way was hypothesis testing. So if we're estimating it, we have to compute our confidence interval. There's a 95% confidence interval for mu. Or we could use our hypothesis testing where we defined competing hypotheses about the null hypothesis and the alternative hypothesis. We always assume that the null hypothesis is true. And if the observed data are rare under the null hypothesis, which was 0.05, yes. So if it was less than 0.05, we can reject the null and then we can conclude support for the alternative, which would be failing to, look at that, failing to reject the null. It seems like a lot of words, but just think about it intelligently, right? Conceptually, and just read this chapter of the textbook, read Unit 5, and just really think about what it's saying and how we're taking these big, broad research questions and we're taking in them and making them very simple statistical questions so that we can do some math and answer and see what did my intelligence assessment work, did my intelligence training work, right? This huge project that some researchers spent, a whole semester doing. We turn it into a couple of equations when we get those results, and we can say whether or not their assessment or their training worked. Crazy. Big concept, little lecture. So hopefully this makes the book make a little bit more sense, but it's a great textbook. So I'm just here to help you with that. And then I will post another video working on some of the problems so that you can kind of see how we would work through problems like that. But reach out if you have any questions. Otherwise, I'll see you next time.